In October, we were very pleased to hear that two ex-Birmingham theoretical physicists had won the Nobel Prize for Physics. Mike Koslitz and David Thouless discovered an extraordinary thing back when they were in Birmingham in the 1970s. It was a very novel and unexpected type of phase transition. Now, to understand what a phase transition is, it's good to have a concrete example in mind. And think about steam condensing into water, or water boiling into steam, or water freezing into ice. These are examples of phase transitions. And the Koslitz-Thouless result was about 2 dimensions. Now, you might wonder what's different in 2 dimensions. You might think everything is simpler, but in fact, it's the other way around. For example, if you were in 1D, you couldn't make a cup of coffee. There's only steam, no kettle can boil. In 2D, it's a little bit more subtle. There, the thing that disappears, for example, are things called soft magnets. Now, soft magnets are rather crucial in today's technology. For example, you couldn't have a mobile phone charger without them. And in fact, you couldn't even have the power grid. So the world would be much more 18th century if we were living in 2D. Now, this experience had been formalized into a result called the Mermin-Wagner theorem that almost all phase transitions didn't occur in 2 and 1D, with one rather boring exception. And what Mike and David discovered was there was a loophole in the assumptions of this theorem. It wasn't wrong, but there was a loophole. And that loophole led to an extraordinary thing. Now, a clue as to that extraordinary thing is the photograph you're now seeing. The picture you can see is of a whirlpool off the coast of France in the Atlantic off Saint-Malo. And you might wonder how this can be the ingredient in the Koslitz-Thouless theory. After all, your experience, since I've been talking about 2-dimensional liquid films, your experience of those in the everyday life might be a plate after you've washed it up. And the fact there's a film of liquid that doesn't flow very easily off that plate and then has to evaporate. But this is where super slithery helium comes to your rescue. It is a material which at low temperatures flows down to atomically thin films. So if you were doing your washing up in liquid helium, as soon as you pulled the plate out of the washing up bowl, it would be dry. So it's a very different type of material. And there you can have these little whirlpools in 2D. Actually, there is also a connection here with Birmingham. The first person to show that these whirlpools exist in helium was Joe Vinan, who is a member of staff here in Birmingham. So, back to Koslitz-Thouless. So the picture of their transition in terms of these whirlpools is the following. At very low temperatures in your helium film, you have a clockwise and anti-clockwise whirlpool stuck together. And they're stuck together because that minimizes the kinetic energy of the fluid motion. As you heat up the superfluid film, the whirlpools, the clockwise and anti-clockwise whirlpools start to get further and further apart because you're providing thermal energy to do that. And eventually they break up. And that is the Koslitz-Thouless phase transition. And the superfluidity, the special aspect of helium, ceases at that temperature. And it becomes much more like the water in your washing up bowl. The Koslitz-Thouless result burst onto the world of condensed matter physics and statistical mechanics, the people who study phase transitions in the early 70s. And there were experiments then done in the United States a few years later that confirmed beautifully that Mike and David's results were correct. But in fact, more was to come. The subject actually had an impact rather beyond those areas. And one place was elementary particle physics and the theory of quark confinement. So you probably know that if you look at something like a proton or a neutron, you have quarks inside, 3 of them in those cases. And those quarks can't get away from each other. And in fact, you can't even pull them apart if you apply a lot of force under normal conditions. So this sounds a bit like the vortex and the anti-vortex, or the clockwise and anti-clockwise whirlpools in Koslitz-Thouless. At low temperatures, you can't pull them apart. So this picture, and in fact the calculation, suggested to the elementary particle people that at very high temperatures, the quarks could separate, and you could get something called a quark-gluon plasma. And in fact, one of the architects of that theory, Stanley Mandelstam, is another ex-Birmingham theoretical physicist. Now, this brings me up to the current time. So in the school at the moment, we have people working on the ALICE experiment at the LHC and CERN, and they reproduce the conditions of the Big Bang at early times when the quarks can actually be liberated from inside the nucleons. And the UK effort in that experiment is led by David Evans and Peter Jones from this school. And in fact, there is another line of continuity with the past, which is that the two new people arriving in the theory group, Hannah Price and Kurt von Keyserlingk, both work on topological physics. Slightly different physics, but related actually to some of the work David Thouless did that was also recognized in the Nobel Prize. So topological physics, Birmingham invented it. Birmingham has been developing it over the last 40 years, and the new people arriving here will be driving it in new directions in the future.